Okay, welcome back. This is now 10.5. So we're still going to be working with trees, but just special kinds of trees, binary trees and rooted trees in particular. So let's take a look here. I have 10 point, I think it's 5, rooted trees. And we begin with a bunch of definitions. The definitions are pretty straightforward. Um, First, we need a big, ugly tree to play with. So let me draw that out. This will take a bit of time here. Just bear with me. Okay. Oh, crud. I already screwed it up. Frick. Sorry. Gosh. Okay, so and then that's going to go down to here. And 1, 2. Okay. So down to here. One more. And this goes to 2. And this guy goes to 2. And then this guy goes to here. Three. Middle guy goes down 1. And then 2. And 1 more. And then finally this guy goes to 2. Over here. And then down 1 more. Okay. I'm going to label them starting with A, B, C, D, etc. F, G, H, I, J, K, L, M, so L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, and they give you a bunch of questions. There's problem one, at least it used to be one. First, what is the level of vertex n? Okay, so level is kind of, here is level 0, okay, at A. And then you can kind of see B, C, and D are kind of aligned. That's level 1. And then E, F, G, H, I are kind of aligned. That's level 2, etc. Okay. So the level of n is 3. Okay. What's the level of A? The level of A is 0. And because of that, it's called the root. Okay, so A is the root. What's its height? The height is the highest level, the maximum of the levels. In this case, it's 5. And the children of n. Those are the immediate vertices that are going below directly from n. So if we find n on the graph, its children are going to be u and v. Okay. The parents of g. In this case, it'll just be parent. Identify where is G? Find it. Where are you? It's right here. So the parent of G is D. And siblings of J. Okay. Those are all the guys that are on the same level as J and descended from the same parent. Okay. So where is J? J is over here somewhere. And so K and L will be its siblings. Notice M and OP are not. Okay, just K and L. siblings, descendants of F. Okay, so this is like everybody that emanates from F, the children plus all of their children. Okay, so where is F? I'm going to find you right here. So we'll have M, S, T, X, and Y. Okay. Okay, so some definitions there. What can we do with binary trees? Well, definitely in computer science you can do a ton of stuff. Let's define a general binary tree. This is just a rooted tree where there's at most 2 children. Okay, so a rooted tree such that every vertex has at most 2 kids. Okay, so you can do math. Okay, you can program math doing this. So you just follow PEMDAS. Somebody gives you a problem like represent A divided by B minus C times D. Okay. In this expression, the overriding, and usually it's parentheses, do parentheses first, then exponents, multiplication, division, addition, subtraction. The division symbol is considered to be a parentheses, believe it or not. It's something that divides it into 2 pieces. So you would have to do A separate than the B minus C times D. Okay, so on one hand you have A. On the other hand, what do we have to do over there? So there's 2 sides to this story. There's the B part, okay, on one side. And on the other side you have a product of C and D. Okay, so we would have to do a product of C and D. Okay. And yeah, so that would represent, this tree would represent this little math expression. Okay. There's some theorems in here. It's just a couple of theorems. There's not much really to do in this section. Let's look at some theorems. Section 3, I guess. The first theorem is, clearly I don't want to use B. The first theorem kind of relates internal vertices and terminal vertices. So if K is a positive integer and T is a full binary, okay, so a full binary tree means that all of the vertices that are parents are going to have 2 offspring. Okay, so an example of a full binary versus just your regular binary tree. This thing is a full binary, okay, as opposed to something like this, where you just have 1 child coming from this vertex. Okay, so that's what they mean by full binary. Hopefully that's understandable. Okay, so if you have a full binary tree with K internal vertices, if you remember the definition of internal vertices from last time, that's where the degree of that particular vertex is greater than 1. Then T has 2K plus 1 total vertices, and K plus 1 terminal vertices. Okay, So going over with this example here, so again, this second, the bottom example is not a full binary. Okay, so let's kind of cross that guy out. Look at the top one, though. The internal vertices are where? Let's circle them in blue. Okay, so this is internal, and the root is actually internal. Okay, so if we wanted to know how many vertices there are, then you just take 2 times the number of internal ones, which is 2, so I got 4 plus 1 extra. So I should have 5 vertices, and certainly if you count them all up, that's kind of what you have, right? So it's 1, 2, 3, 4. Yeah, there's 5. 2 times 2 plus 1 is 5. Okay, so it seems to work, right? The book will go and try to convince you of this and kind of play around with it a little bit. Say we know the total number of vertices will equal the number of vertices with parents plus the number of vertices that don't have parents. Okay, so the number of vertices with parents will just be 2 times the number of parents. Okay, so 2 times the number of parents. And the number of vertices without parents, there's only 1, right? And that's the root. So you can also think of parents as internal vertices. So this will just be then 2 times the number of internal vertices plus the 1 root. And of course, the number of internal vertices in this theorem is given by k. Okay, so k internal vertices. So this will be 2k plus 1. And then how did they get that extra part? So how do they know it has k plus 1 terminal vertices? Well, you can kind of play this game again. You can say, all right, the total number of vertices must equal the number of internal vertices plus the number of terminal vertices. Okay, so the total number of vertices from the previous work is 2k plus 1. We're given the number of internal vertices to be k, and we just want to figure out what's the number of terminal vertices. So it's an unknown that we can solve for here, and if you subtract k from both sides, you get the number of terminal vertices to be k plus 1. Okay, so no big deal there. In the book, they'll kind of use it in various exercises. For example, number 7, they'll give you characteristics of a hypothetical tree, and you have to determine whether it exists. And if it does exist, then draw an example. So number 7, you have a full binary tree with 12 vertices. Okay, so does this thing exist or what? So if you look back at our theorem, if you have a full binary tree with k vertices, then T has 2k plus 1 total vertices. So in that case, we should be able to rewrite 12 as 2k plus 1, right? And so how many internal vertices do we have? There has to be an issue right there, right? So the theorem kind of tells us that if you have a full binary tree, it's a corollary. Your number of vertices will have to be odd, okay? So as corollary from the above theorem, full binary trees have an odd number of vertices. And that's the way the cookie crumbles, right? Okay, so let's get on to the other theorem that they give us. Let's see what section I'm on. theorem. So the second theorem, this is the last theorem in this section, I think. This theorem says for all h greater than or equal to 0, if T is any binary tree with height h, and T terminal vertices, then the number of terminal vertices will be less than or equal to 2 to the h power. Okay. They also give you another part that's like just take the log of both sides, but we're not going to use that. So the theorem, the way they prove this is by induction, and I'll kind of try to sketch that out a little bit. So proof, the basis step first, note if T has height h equals 0, then it has just one terminal vertex. It's the trivial tree, right? And that thing is terminal. It has one vertex which is terminal. Okay. So if we plug 0 into that inequality, which we're calling now P of k, so P of 0 is, so back up here, I guess maybe it's P of h. P of h is kind of this statement here. So P of 0 is going to be saying that 1 is less than or equal to 2 to the 0. Clearly this is true. Okay, 1 is equal to 1, so therefore 1 is less than or equal to 1. Okay, so clearly this holds. All right, so then we go to the inductive step. We're supposing then all of the stuff we need. So T is an arbitrary binary tree. H in this case is greater than 0. Suppose H is greater than 0, and P of k is true, right? So T is less than or equal to 2 to the k. We want to show that T is less than, when you have a tree that has height h plus 1, or in this case k plus 1, the number of terminal vertices T is less than or equal to 2 to the k plus 1. Okay, it's pretty easy. There's just two cases, and I'll kind of do them side by side here. So case 1, where the root is considered terminal, so it has just and there has to be more than one. You can't just have the trivial tree, right? You can't just have a vertex, so it has to be coming down to something. And then imagine, it has some baloney down below it. Okay, so if you kind of just look at this part of the tree, in this case, that tree will have height h, or height k. Okay, so this is a tree with k, with height k. Overall, the entire thing has height k plus 1, but this tree has height k. So we could say its number of terminal vertices will be less than or equal to T. So because of the inductive hypothesis, the number of terminal vertices is less than or equal to 2 to the k. So then if you kind of go out a little bit to include the root, in that case, this is a tree now with height k plus 1, where the number of terminal vertices t is less than or equal to, well, the number of terminal, we can work with that inductive part, right? So there's only one more terminal vertex, the one that we excluded from the white dashed circle, right? So we know the number of terminal vertices in the white part of the the tree without the root is less than 2 to the k, and the tree with the root, there's only one extra terminal vertex, and that's the actual root. Okay, so in case 1, the root is terminal. Is a terminal vertex, so we kind of can just tag that on to the 2k, and then 2 to the k plus 1 is less than or equal to 2 to the k plus 2 to the k, because k was assumed to be greater than 0. We could also say it's just strictly less than, I think. But anyways, 2 to the k plus 2 to the k gives you 2 to the k's, and then 2 times 2 to the k is just 2 to the k plus 1. Okay, so that's our first case. And the second case, so note case 2, where the root is not terminal, so it won't add anything into that inequality. And you could kind of just exclude it and not even worry about it. So in the not terminal case, let's again draw the picture. So now it's binary. You only have 2 things coming down from it. And then we have some other tree that's imaginary. I don't know what it does. Okay, but it's a binary tree, and I believe it's yeah. Okay, it's not necessarily full though, right? Okay, so in this case, what you want to do is kind of just exclude the root and work with these 2 trees that extend from the root. Okay, so there's one tree here, and I just circled in yellow, and in that case, it's a tree, again, of height h, so I can use the inductive hypothesis. Okay, so with height h, so by the inductive hypothesis, the number of terminal vertices on that will be less than 2 to the k. And then there's this other tree, which I'll circle in red here. On that guy, this thing has, it's a tree, again, with height h, or height k, I guess, they should be k's. Okay, a tree with height k. So again, the number of terminal vertices on that tree will be less than or equal to 2 to the k. All right. So the total number of terminal vertices, which you can just add the yellow terminal vertices plus the red terminal vertices together and call that t, so some other t value. Hence, the total number of terminal vertices will be less than or equal to the bound of 2 to the k from the yellow tree plus the bound of 2 to the k from the red tree. Okay, and again, 2 to the k plus 2 to the k is equal to 2 to the k plus 1. So in either case, you have the inequality that we were trying to prove. The number of terminal vertices is less than 2 to the k plus 1, which is what we were trying to prove. Okay, the last section is on the binary search tree. Okay, so the algorithm's given in the book. I'm just going to kind of walk you through it rather than actually follow the algorithm. So I think this is section 4 in my notes, maybe. The binary search tree. Okay, so how does this go? They're going to give you a list of numbers, and you're going to build a tree such that all of the numbers to the left are less than the sort of root, and then all the number on the right are greater than the root. Okay, and it keeps going like that. Okay, so I'll just give you some examples, and I hope you could sort of catch how the algorithm works. So they're going to give you a list of numbers, and you're kind of going to embed them into a tree. Okay. Okay, so you start with one vertex. The algorithm will call it V. Okay, and you put 15 in that vertex. Okay. Then you go to the next number in your list. Okay, so 15. Now I'm going to 10. And ask yourself: is 10 less than or equal to, or sorry, is 10 less than 15? It doesn't really tell you what to do if it's less than or equal to. I guess you just put it in the same place. But if it is less than 15, you add a vertex and an edge. You add an edge and then you add a vertex to the left. Okay, and then you're going to put, in this case, because there's no vertex that's already sitting there, you're going to put 10 in that position. Okay. Okay, and as soon as you put it into its position, you're kind of done. You jump back out of the while loop and you repeat. Okay, so again, you start back at 15 now, and you ask yourself: is 19? How does 19 relate to 15? Right? So 19 is greater than 15, so you're going to add an edge below 15. There is no edge, so you add an edge below 15, and then you're going to add a vertex there and put 19 in there because 19 is greater than 15. And so then you jump back out of the while loop and you start over. Right? So you compare 15 to 25. You say, okay, 25 is greater than 15, so you look below number 15. Okay, number 15 already has kind of a vertex there. So what I'm going to do is say that now this is my sort of comparison vertex. So I'm kind of jumping to 19 and comparing that to 25. Okay, so at 19 I say, well, 25 is greater than 19, so I'm going to add an edge to the right and then make a vertex where 25 is in there. Okay, and then that jumps me out of the loop and I go all the way back to 15 again. Okay, so I compare 15 to 12. 12 is less than 15, so I go to the left. There's already a vertex there. Okay, so I'm going to make 10 my new sort of comparison vertex. Okay, so I sort of scooch over the 10. And I say, is 10, and it's getting really busy now, I apologize, is how does 10 compare to 12? Okay, so 10 is less than 12, so I'm going to put an edge to the right, and then I'm going to put this 12 in a vertex to the right. Okay, as soon as I make that vertex and I deposit the number, then I jump out of the while loop and I go back to the original node again, or the original vertex. So I'm at 15 again, and I compare 15 to 4. Okay, so 4 is less than 15, so I look below 15 at 10 at this guy. There's already somebody there, so I make 10 my sort of next, my new comparator, and I compare 10 to 4, and so 10 is greater than 4, so I'll make an edge to the left this time and put 4 right there. Okay, it's a little like riding a bike with these things. Once you kind of get the idea embedded in your brain, it's relatively easy. Okay, so let's do one more example here, and hopefully you'll kind of just be able to get the flavor for it. Okay, so one more example. And of course the algorithms in the book, if you're better at just reading the algorithm, by all means just go with that. Okay, okie dokie, so let's try this. Let's see if I can make it a little more clear. So I'm going to start at 19. Right, that's my main vertex. So I compare 19 to the next guy, 10. 10 is less than 19, so I look below 19. Is there a node there or a vertex? No. So I'm going to put 10 to the left of 19. Okay, then I'm done. I jump out of the loop, go back to 19. Compare 19 to 25. 25 is greater than 19, so I'm going to the right. There's no vertex there. Okay, and nodes are and vertex, I call them, those are kind of the same thing for me. Okay, so I put 25 there and I'm kind of done, so I jump back to 19 again. Okay, so I compare 19 to 4. 4 is less than 19, so I go to the left. There's already a vertex there. Okay, so that becomes kind of the new comparator, number 10. So I compare 10 to 4, and now I say, okay, 4 is less than 10, so I'm going to go to the left and deposit 4 right there, and then I'm done. I jump back out of the loop, back to 19. Okay, so now I'm comparing 19 to 15. 15 is less than 19, so I go to the left. Okay, and now 10 becomes the new comparator. Okay, so 10, I'm circling in blue. I'm now comparing that to 15. Okay, so 15 is greater than 10, so I must be going to the right. There's nothing there, so I construct edge and deposit 15 in that vertex. Okay. Then I'm done. As soon as you make the vertex, you're done with the while loop, and you jump back out, go back to 19, and now we're comparing 19 to 12. Okay. So in this case, 12 is less than 19, so I'm going left. Okay, so the next comparator becomes 10. So let me circle 10 now in green. So I'm comparing 10 to 12. Okay, so 12 is greater than 10, so I must be going to the right, in which case 15 becomes the next comparator. So let me circle 15 in yellow, and I'm comparing 15 to 12. Okay, so 12 is less than 15, so I must be going to the left. There's nothing there, so I add an edge to it, and then I deposit 12 in that vertex. Okay, and that's it. That's the algorithm. And there are questions like that on the test. I'll probably put some on the final. Okay, where you have to just build, and it's fill in the blank. You build it by filling in the blanks. Okay, so you could read the details about the algorithm and the search algorithm in the book, but that will get you started on your way. If you've never seen that kind of thing before, just get in there and feel around how it operates, and we'll see you next time.